Hi guys, and welcome to the week 10 Start Here video. This week you will be getting your big tickets completely graded back, and I apologize it's taken so long to get them back to you. It is quite a process to grade them, and I've had about upwards of 70 of them to grade, so you can imagine it takes a little bit of time to get back and to give you feedback on that that is meaningful. So the revision requirements are posted this week, and you'll be able to start in on those, and those are due April 10th. So back in our modules page, you can see that document there. Big ticket number 1 revision, and I'll let you read about that. Basically, you're addressing the comments that I've put into your document. Basically, the goal is to get you to improve your paper, and then also to be able to increase your score on that should you want to. That's not a requirement, and you don't have to work with your teams on this. You could work individually because each person will be submitting their own revision copy. So if you do work on it with your team, you can certainly submit the same copy among multiple people. However, if you choose to work on it on your own, then you're submitting your own copy as well. So either way, each person that does revisions will be required to submit either the one that they worked on with their group or the revisions that they did individually. With that said, there is a quiz this week, and it's the content from weeks 9 and 10. Last week was the idea of compound interest, and this week we'll be focusing on annuities, which is a really important and interesting concept that deals with basically, we can't really often put away a lump sum of money. We often put away small chunks of money on a regular basis, i.e. 401ks, IRAs, 403bs, whatever tax code there is for retirement plans. So it does involve compound interest. Compound interest cannot be, we can't just ignore compound interest because compound interest is a part of basically all financial matters. The discussion board will be on loans this week. We haven't talked about loans, but the whole goal here is to get you to think about interest and see how it applies to an auto loan and the terms of an auto loan more specifically. Now we'll go ahead and do just a wrap up of the discussion board, which is titled Failure to Comply, and deals with this idea that the CDC has a flu outbreak, and there's been a successful recovery rate of 93%. So you look at a small town and you want to determine whether the rate of recovery is higher in this town than the average of 93%. So you do a random sample, you look at 20 people, and 19 of them have recovered. Now, if you do the math on that, this would result in having a P, which is remember, that's just saying the percentage for the sample. So here's your population, and this has an assumed pi of 0.93. So we just know statistically, for some reason, from some studies, that there's a 93% success rate in the population. But you take this small town that has 20 people in it, so n equals 20, i.e. 20 trials, if you look at it that way from a binomial standpoint, and you find that the sample proportion of people who recover is actually 95%, which is really just 19 out of 20. So yes, the 95% is higher than the national average. However, keep in mind that you haven't sampled the entire town. You've looked at a sample. So from one sample to the next, you expect sampling variability. And that's a very important statistical concept that you'll get in GBS 221 statistics. Sampling variability is the reason we do these statistical tests, because we want to determine whether that 95% is really a statistically meaningful difference from the assumed H0 of 0.93. So when we do this assessment, we assume the null hypothesis. Why do we do this? We do this because it's something that we've assumed is true, that we've known to be true about a population. We're not going to talk about how you get that. That's a whole different process involving sampling and census and data collection, all that stuff. We're just focused on analyzing the data. So we assume this is true. Well, if this is true, we want to assess how likely would it be that a distribution with 93% success rate would result in a sample of 20 with a 95% success rate in that sample. So we look at this, look at the binomial distribution. So we would look at, okay, assuming the mu value, or sorry, the pi value is 0.93, we're going to build a distribution, and I don't know exactly what this is going to look like, but we have the number of successes, and this might be 1, 2, 3 successes, the probability of 4 successes, 5, 6, and so on and so forth. And we want to look at, all right, what is the probability of getting a p-value of greater than or equal to 0.95, assuming or given that pi is equal to 0.93. Okay, so we're going to look at this distribution, and we're going to see how likely it is to get a p-value of greater than 0.95. This translates to x being greater than or equal to 19, where n is equal to 20. So really, we're looking at what's the probability of getting 19 or more recovered people in this sample. So I'm going to turn to GeoGebra because GeoGebra has a nice probability feature that I'll show you. So let me do that. So within GeoGebra, we're going to actually change views here. And within the view option, whether you're using the Google Chrome built-in app for GeoGebra or actually the standalone version like I'm using here, you can select probability calculator. And this probability calculator is really neat because it actually shows you the distribution that you're working with. Now, this is something we'll talk about a little bit later in this class. This is called the normal distribution, and the normal distribution is linked to the binomial distribution. But what we're going to go ahead and do is we're going to select the correct distribution from the list here, which is binomial. And right away, we get some data that pops up here and shows us the different components of the binomial. And in particular, right now, this is actually by default, for whatever reason, set to n equals 20. You can change the sample size here, the number of trials. You did 40, and you can see that how that would look. And over here, we see the probability of achieving 0 successes out of 40, 1 success out of 40. You can tell that if the probability of success is 0.5, then you would expect right around 20 to be your highest. That's your expected value. That's your average of the distribution. So even in a sample that has some variability in it, we probably would expect that most of it is somewhere within like 16 and 24 successes out of 40. But of course, we want a sample size of 20. And we want to model what the null distribution would look like, assuming the success probability is 0.93. Now, we're going to get a gigantic skew here because of the fact that 93% success rate means that you should be getting pretty close to 20 out of 20. And what we can also do here is we can actually either click on probabilities within this window. Where'd it go? Or you can actually have things highlighted in here. So if I click on a probability, like what's the probability of getting 19 or more successes? Well, the probability of getting exactly 19 successes is 35.26% likely. But what we want to know from a statistical standpoint is what is the probability of getting something as or more extreme than we got? So probability of being somewhere in the tail means 19 or 20. So if you click and drag, you can actually highlight both of them. Or you can manually change 19 x is between 19 and 20 here. So the probability of actually observing 19 or more successes is 59%, assuming the null hypothesis, which is that there's a 93% success rate. So even if you got 20 out of 20, your probability of observing that under the null hypothesis would be 23%. Well, wait a minute. We're only going to reject the null hypothesis when the probability of success when the probability of observing what we have observed or something more extreme is less than our alpha, which is 0.05. So unfortunately, even if you got 20 out of 20, you won't be able to reject the null hypothesis. And this is what we call a lack of power. So what can we do? Well, in here, this is kind of cool because you can just change the number of trials and really just look at the trick here is to look at the very last tail probability. Because if you get the maximum number of successes and your probability of that is 21.78, even if you got 21 out of 21 successes, you couldn't reject the null hypothesis. So we keep going up. We could try 22, see what that would look like. And still the probability of getting 22 successes is getting lower, 20.26%, but still we wouldn't be able to reject the null hypothesis. So let's bump this sucker up and make it 30. And with 30 trials, the probability of getting exactly 30 out of 30 is 11.34% chance. Again, assuming that 93% of people are known to recover fully from this flu. Still not sufficient, so let's bump it up to 40. So what's the probability of getting 40 out of 40? Well, it's pretty close to our alpha, which is 0.05, but even if you got 40 out of 40 people successfully recovered, you wouldn't be able to reject the null hypothesis. Okay, so let's change this to maybe 50 and see what happens. Well, if we have 50, you'll notice that the tail probability of getting 50 out of 50, if that were the case, then that's very unlikely under the null hypothesis. That has only a 2.6% chance. And we would reject the null hypothesis and say, yeah, we believe that this town has a higher recovery rate than the general public. Now, this should make sense because with small sample sizes, all kinds of various things could happen. You could get one person who is extremely different than the rest, and it really skews the resulting data. So we've gone maybe too far because I went from 5.49 to 2.7%. So I'm going to bump this thing down and maybe try 45 because I just want to figure out the minimal sample size in order to be able to reject. Well, with 45 people, if I got 45 out of 45 recovered people, I would still be able to reject the null hypothesis. So let me try something smaller, maybe 44. And the second that jumps above 5%, then we know we're not going to be able to reject the null hypothesis any longer, and we have no power. That's still pretty close. Let's see if I can reduce the sample size to 43, and I still can do that. So let me try to go down to 42. And with 42 people, yep, I can still reject if I got 42 out of 42. And how about 41? We know 40 has a too high of a tail probability. 0.04, oops, didn't change, should be 41. So if I observed in a sample 41 out of 41 people recovered, I would still be above my rejection criterion, which is I'm only going to reject the null hypothesis assuming I observe something that's 5% or less likely. So it looked like 42 was the minimal sample size we could have to have any statistical power whatsoever. Now, that's not necessarily a good thing. This doesn't say, well, let's get 42 people in the sample. This just gives us a baseline. This says if we want to even have a possibility of rejecting the null hypothesis, we'd have to get 42 people in the sample. Now, so you'd have to really have an extreme case in order to get exactly 42 out of 42, because of, again, sampling variability. So we might want to try to sample as many people as possible given our budget constraints. So if we sampled 100 people, then let's see. Well, yep, if I got 100 out of 100, I could reject. Okay, we notice that 99 or 100 would still put us well below our alpha. But eventually, that probability gets too high, 0.0744. So as long as I had 98 or more successfully recovered people in a sample of 100, assuming the null hypothesis is true, I could reject the null hypothesis. And again, that's still not very much statistical power because that only gives me 3 possible values in which I would be able to reject the null. So hopefully this gives you some insight into doing this process. Now, there is a mathematical way to compute power, and power is something we're using loosely here. It's well-defined in statistics, but this is good enough for us to get to think about and use the tools we've developed for the binomial distribution and the binomial hypothesis test. So that's it. Have a great week, and I look forward to seeing you again in this week's discussion board.